you were asking earlier what would be the focus. I wouldn't say these are the focus, but these are definitely the most sort of commonly used tests, the ratio and root tests. So they're new tests for divergence. And I think I'll just state the ratio test and then give you an idea of what the proof looks like. But all right, so here's the theorem. We call this the ratio test. Okay. And the reason this is nice is we don't have to look at the terms and think, oh, it's acting like this or it's doing this. It's just a test that uses just the terms that you're given. So let A sub n be a series. Okay. No assumption that the terms are positive or whatever. We don't need it to be an alternating series. It's just any arbitrary series. Okay. And we do want non-zero terms with non-zero terms. If you think about what is an infinite series, it's just adding stuff up, right? And so if you add in zeros, that's kind of silly anyways, right? Adding in nothing doesn't do anything. So you could always say, okay, well, let me just apply this to the non-zero terms. And as long as that works out, it's fine. But again, for the most part, we're just going to look at things that have non-zero terms. And then we let L equal the limit as n goes to infinity. And so here's where the ratio test name comes in. Okay, you have your series A sub n, you take the n plus 1th term and you divide it by the nth term. And then you get a limit. Now I write that L equals that. That limit may not exist. That limit may be infinite. Okay? And so we'll incorporate that into our answer here. Okay? So then you just have 3 conditions. If that L is less than 1, okay, and that includes 0, right? So notice we're taking absolute value, right? And so it's going to be a positive number or possibly infinity or just some other thing, but it's definitely positive. And so if it's less than 1, including 0, then your series converges, and doesn't just converge, but it converges absolutely. And remember, last time we said, well, what was the definition of absolute convergence? Was that the sum of
the sum of the absolute value of an.
right? And so what we're saying is not only does this converge, but the sum, if you put absolute values in, converges, right? And that what we had a theorem at the end of class last time that was a stronger condition. If it's absolutely convergent, it's convergent, but it might not be convergent otherwise. Okay? And so this test only lets you conclude that if L is greater than 1, then your series diverges. Okay? So if either one of these conditions are done, you're completely done with the problem. So when you see the problems we're going to look at, they're going to say, determine if the series converges absolutely, diverges, converges absolutely, converges conditionally, or diverges. If you get either one of these answers, you're completely done with the problem. The tricky spot is the third condition, which is if L equals 1, then this test fails. Okay, so that's sort of the cutoff spot. And then you have to go back and use other tests that we've already talked about. So when you see problems in general, we'll either use this test or think about whether this test applies. And then if this test fails, then we have to move back to our comparison test. But it's almost always nicer to do this test if possible. And so I'm not going to go through the full proof, but let me just sketch a tiny piece of what's going on. Okay? So I'll just say the idea of the proof. And we'll just say of R1 there. Okay? So suppose the limit as n goes to infinity of this equals L, some L that's less than 1. So that's the assumption for parabola, right? You got some series where the limit of the ratios of the n plus 1th term and the nth term is less than 1. Okay. So now if L is less than 1, then you should be able to squeeze some number in between there, right? On the real line, if you got any two numbers that aren't equal, you can squeeze a number in between. And so there exists an R such that, you guys, have we used this?
I don't think so.
Okay. That stands for there exists. Maybe I should just not use it. No, I won't use it in the future. Try not to use it, but that's a common math symbol. We'll common. So there exists an R such that L is less than R is less than 1. Right? So you have it in there. And so again, what does the limit being L mean? It means the terms get closer and closer to L, right? And so if we know the terms are getting closer and closer to L, we can assume they get less than R because R is bigger than L. Does that make sense? And so, and then, I'm going to write it again. There exists a capital N, okay, such that if n is greater than or equal to capital N, right, then these terms, right, in that limit get less than R. That's what I just said, right? Before. And so here's what that really looks like. So when little n is capital N, we get this. So what's true? A sub n plus 1 is less than a sub n times little r, right? And then you apply it again, an plus 2 over an plus 1, right? That's just your next term is less than r as well by this statement, right? It's true for every n bigger than there. But then that becomes an plus 2 is less than an plus 1r, but an plus 1 was already less than that, and so this whole thing is less than an r squared. Does that make sense? And again, I won't go through the details, and I don't want you to worry about the details, but you can just show that in general, an plus k is less than a capital N r to the k. And again, notice that capital N is a fixed number, right? I fixed the capital N. So this is just some number, and now we're saying the tail end of our series is smaller than a number times r to the k. Well, what kind of series is that?
Absolutely convergent.
Right, because it's a geometric series, right? If you looked at the sum of that, that's a geometric series because you're just putting higher and higher powers of r. And it's a geometric series with r less than 1. Does that make sense?
Okay.
And so it's really you really have to say now by the direct comparison test, blah, 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 blah. But that's the idea of the proof, is you can make your terms smaller than this geometric series, and it's a convergent geometric series, so you get convergent. So again, I won't put out all the details, but therefore,
So the geometric series has to be greater than L for it to.
well, so if L is less than 1, then you can squeeze this R in here.
Okay.
And then that forces that R is less than 1, so your terms are eventually less than the terms of this geometric series which converges. If your L is bigger than 1, you'll be able to squeeze the R on the other side, and then you'll be able to make everything bigger than something that's bigger than 1. And then, right, if that R is bigger than 1, it'll go off to infinity, it won't converge. And so you'll kind of flip, all your inequalities will just flip around to do the proof of part 2. And then you can see that, right, if this is 1, we don't really have any information. It's not helpful for whether this thing converges or diverges. But anyways, therefore this converges absolutely. Okay. So, don't get bogged down by the proof. This is the theorem, let's just apply it And let's do a real quick one, and I'll just squeeze it in over here so we can leave it up on the board one more time. Okay? So, let's just do converge or diverge for now. We'll come back and do some with absolute convergence. Here. Okay, so this is kind of the standard place where you're going to see, where you're going to want to use this ratio test. Anytime factorials come into the game or exponentials come into the game, the ratio test is really efficient at figuring things out. Okay, so let me just, you don't have to do this in the future, but let's just write it out. So for this example, what's our a sub n? Just this, right? It's not a trick. That's your a sub n. What's your a sub n plus 1 then?
Just 3?
No. Replace your n with n plus 1, right? So 3 to the n plus 1 divided by, replace your n with n plus 1, n plus 1 factorial. That make sense?
Why would you, why would it be n plus 1 factorial? How do you replace?
It's just like if you had a function, right? If you have your function f of x was 3 to the x over x, well, let me do it this way, over x cubed, right? And if I said, what's f of 2, right? You're just plugging that in for your x. That'd be 3 squared over 2 cubed, right?
Yeah.
Now if I said, what's f of y? 3 to the y over y cubed.
Oh, okay. I
So
see.
what's f of x plus 1? Right? 3 to the x plus 1.
Okay, yeah, your
That
n
makes
plus
sense.
1's your variable, so you're just,
Yeah.
okay, that's what it is.
Does that make sense?
Yeah, I didn't see that for some reason.
It's okay. And it's a little bit awkward when you're looking at series or sequences, but remember, they are just functions, right? And so whatever that subscript is behaving just like your input into a function. Okay, so now the test says, let's look at the limit of the ratio of those two things, right? I'll move over here. So now you just do the limit. N goes to infinity, and I'll just write this out. So it's 3 to the n plus 1 over n plus 1 factorial divided by 3 to the n over n factorial. You got to be very careful. You got to realize it's a to the n plus 1 on top. Otherwise, you're going to get the opposite answer every time. So keep the right ratio. And in this case, we don't really need the absolute values, right? Everything's positive inside there, so I'll drop that from now on. And usually, we don't even bother writing this line, because what is it? If you have a fraction and then you divide by another fraction, you can just multiply by its reciprocal, right? So we usually will just start off with taking our a sub n plus 1 and then multiplying by the reciprocal of a sub n. Does that make sense? And it's going to be all this same sort of cancellation that keeps happening. I think we might have already had a little bit of this happen, but let's, what happens with the 3's?
Cancel.
They cancel and leave you with 3 in the numerator, right? You got one extra 3 up top. So this leave you with a 3. And what about the factorials? Just leave you with n plus 1. Right, again, I'll just, if you're having any trouble seeing it, it's n plus 1, right? And then n factorial. So that bottom one is that, and the n factorials cancel, and you're just left with n plus 1. What's that limit? 0. Is 0 less than 1, greater than 1, or equal to 1? It's less than 1. So what's our conclusion? Therefore, our series, which is what, 3 to the n over n factorial, converges. And I'm just going to go ahead and say absolutely. Right, you were just asked if it converged or diverged. But that's what I think. that make sense? So that's the basic idea behind the ratio. Just apply it to there, and so let me give you two of them and have you try to work some of these out. Okay. So, take a minute, you'll need more space than I'm putting up here, I'll move it around in a minute. But take a second, try to do both of those, so again, oh, it doesn't really matter where this sum started. Take the ratio of the n plus 1th term over the nth term, take that limit, and then again, you just compare it to 1. And see what you end up with. I'm going to start slowly writing these up, but just to keep working on it. Okay, so let's talk about that first one. Everybody getting this right? You plug in n plus 1 in, so you get n plus 1, n plus 1, n plus 1, right? And then you're dividing by this one, and again, that's the same as just multiplying by its reciprocal. So. All right, now we start canceling things. The same stuff happens with the 3's, right? And we just are left with a single 3. I realize I used 3 way too much. It's the greatest number. So we'll get that 3 in the bottom, right? And then we're taking absolute values, and so you could think of the negative 1's canceling each other out, but it's absolute value, so that we can just ignore the negative 1's altogether. Does that make sense? And then what about the n, the other bits there, the n plus 1, plus 2, and the n plus 2? Well, they don't exactly cancel out, right? But we can write that as n plus 3, and then just n plus 2 like this. That make sense? Now, what's that limit? 0. No. Right? It's n and n, so 1/3. Does that make sense? And again, what do we compare that with? 1, is it less than 1?
So absolutely convergent.
Yep. So therefore, your series that make sense?
Why does, when we plug in n plus 1 for n,
Mhm.
why do we plug in n plus 1? Is that just because n's equal to 1? Or why exactly, where does?
Well, no, I mean, so it doesn't have anything to do with that starting point. I mean, it really comes down to the proof that I had up here earlier, is that if we look at that ratio,
Yeah.
right, and we can show that that ratio is less than 1, then we can compare it to this geometric series. But that's all sort of happening behind the scenes. And so we're just saying, here's the theorem. If you take this ratio, and you always just use the n plus first term over the next term, and so it's basically just showing if this term gets smaller than that term really fast,
Yeah.
right, that's when you're going to be less than 1. So when this gets tiny compared to this, that's when you'll get stuff that's less than 1, and so you're concluding convergence there. Okay, so let's try the other one, and again, there's not enough space, so I'll move over here. So with this one, right, I'm going to just do again, limit as n goes to infinity. Again, n plus first term, what is it this time? So for that C there. -1 to the n plus 1 plus 1, I'll just say n plus 2.
Okay.
That make sense?
Yeah, and then n plus 1 factorial,
n plus 1 factorial, good. All over
n plus 1 squared plus 3.
n plus 1 squared plus 3, good. And then times
Let's see,
n squared plus 3 over.
yeah.
Yes, a reciprocal of that, so n squared plus 3, good, over -1 to the n plus 1, and then n factorial, right? Does that make sense? So just flipping this over.
Oh,
You're really dividing by it, but they're almost always fractions, and so it's convenient just to start off like that. All right. Again, we're taking absolute values, so we just ignore the -1s. The n factorials do what?
cancel,
Cancel, leaving you with
n,
n plus 1, right?
Yeah.
N plus 1, and then so this cancels that factorial bit, but you still get that n plus 1 up top, right? And then there's really not much more you can do here. This is still going to be what? N squared plus 3. And then you could multiply this out if you want, but I just say this, n plus 1 squared plus 3. So you get to this point. So now, when we look at this ratio, what kind of polynomial, what's the degree of the polynomial in the numerator? It's n cubed, right? If you multiplied it out, you get n cubed. What about the denominator?
n squared,
N squared. So if you have an n cubed up top and an n squared on the bottom, what are you going to go off to? Infinity, right? It'll be n cubed over n squared, it'll be like n.
yeah.
Does that make sense? And so this is infinity.
So it never,
Infinity is greater than 1, right? That's a silly thing to write on the board, but I'll write it up there.
if the answer ends up equaling 1 and the test fails, what do we write, does not exist?
No, so that's what we'll do in a minute here.
Okay.
That's when we then have to fall back on our earlier tests that we had.
Oh, okay.
So the idea is, we'll use these guys when we can, but when these fail, then we'll have to use the comparison test. And they essentially fail when you have polynomials. They work if you have exponentials or factorials, and then this test fails if you just have polynomials. But anyway, so anyways, this is greater than 1, therefore our series over n squared plus diverges. Does that make sense?
Yeah.
Okay. Let's do one more before we move on. So this one will have some goofier algebra in it. The idea is still, oh, and I guess before I move on to, let me just point out this one. So if you look at this one, right, you have n factorial. What's that? N times n minus 1, n minus 2, n minus 3, n minus 4. So once n's bigger than 2 or 3, that's really bigger than some huge polynomial, right? Because you get n times n minus 1, so that's n squared already, times n minus 2 is n cubed. And so this is giant compared to this, right? And so you could have just used the nth term test and said, those go off to infinity and I'm done. This test has sort of the nth term test built into it. So every time you conclude divergence here, the nth term test would have worked. But sometimes it's hard to see when you have, you know, factorials and exponential bits. And so I wouldn't get too bogged down if it's not, you know, polynomial over polynomial or polynomial over an exponential. I wouldn't worry about the details of the nth term test. I'd just sort of jump to the ratio test and try it, because it kind of gives you everything for free. Okay, so same setup. This time everything's positive, right? So I'm going to just drop the absolute value. What does my n plus 1th term look like?
N plus 1 to the 5th, and then 2 times n plus 1 factorial.
That makes sense? And then what's the nth term, or the reciprocal of it? Just 2n factorial on the top, right? Over n to the 5th. Okay. And so this is where you have to be a little bit careful. You can't simply do what we were doing before, which was cancel out that factorial, because this term is really, you're going to, let's just work it out. So I'm going to do this. I'm just going to put the factorial bits together, and I'll put the other part together. Does that make sense? Let's multiply the 2 through, I get 2n plus 2, and so I moved the denominators around. Okay, so before we even worry about the factorial, let's just think about what's going to happen. As n goes off to infinity, what's n plus 1 to the 5th over n going to do? It's going to go to 1, right? That's a 5th degree polynomial with a coefficient of 1 over another one. So that'll just go to 1. Or you can think of it as n plus 1 over n to the 5th, right?
Yeah.
And so that'll go to 1 to the 5th. So this whole bit's going to go to 1. So it's really just this that's going to control what happens. And then again, off to the side, let's talk about this. What's 2n plus 2 factorial equal? It's 2n plus 2 times what? 2n plus 1 less, so that's 1, right? Times 2n, and then so on, so that tail bit is 2n factorial. Does that make sense?
Yeah.
So when we cancel those out, what are we left with? 1 over. We get those 2 pieces still left over. Does that make sense? So we get, I'll just write it out. So we have 2n factorial, and then again, this is 2n plus 2, 2n plus 1, and then 2n factorial. And so those factorial bits cancel, but you're left with the rest of that. And so now, you can reason this out however you want. I'm just going to say this. Fifth degree polynomial in the numerator, what's the denominator?
5th, or n to the 5th.
Well, n to the 5th, but times 2n and another 2n, so what's the degree going to be down there if you multiply it all out? So it'd be a 7th degree. You have 5th plus 1. So you'll have a 7th degree polynomial in the bottom. So 5th degree polynomial over 7th degree polynomial, what's it going to go to? 0. So this whole thing goes to 0, less than 1. Therefore, our series is absolutely.
And if we use the nth term from the start, like we are going to get it to 0.
Right, so that one would go to 0, but again, knowing it goes to 0 isn't enough, right? If it doesn't go to 0, it diverges. If it goes to 0, you're not sure. Because remember the harmonic series, the terms go to 0, but it still diverges, right? And so, like I said before, if you see factorial or if you see an exponential, I wouldn't even bother worrying about the nth term test right away. I would just try the ratio test and see what you come up with. It's usually easier than doing anything, and it's, you know, it's really simple to make a little mistake where you think something converges or diverges.
So these problems will be like mixed up with like, you know, something you'd use the P-series test or geometric series
Right,
test,
and
so you
that's-
just have to know.
That's what we're gonna do right now.
Okay.
So this is what you're generally gonna see. Determine if the following, sometimes I'll give you a heads up as to what test to use, but most of the time it's left pretty open. The one exception is I'll always tell you if I want you to use the integral test. Otherwise, you'll go through the same series of tests. So determine if the following converge, absolutely, converge, conditionally, or diverge. All right, so let's just start with Okay, so the ratio test is going to fail when we try this one, but let's try it and see how it fails, okay? And then we'll go on to whatever else. So this is, so when you see this one, if you see this on a test, you'd see polynomial over polynomial, there's no exponential, there's no factorial, that's when the ratio test is gonna fail, and so you wouldn't even use it here. You would wanna try the nth term test though, right? So, is the nth term going to go to 0? Yeah, you got n squared over n to the 4th, right? So it's going to go to 0. But let's try the ratio test. Try ratio test. Again, eventually we'll avoid it for problems like this, but just a nice easy example to see it fail. So, what's the n plus first term? It's n plus 1 squared, right? Over n plus 1 to the 4th plus 1 times the reciprocal, so n to the 4th plus 1 over n squared. All right, now don't get bogged down in showing any details, but what you have happening here, right, is n plus 1 squared, what degree is that polynomial?
Squared.
Squared times a 4th degree, so what's the total degree of the numerator?
6.
6. Denominator, n plus 1 to the 4th plus 1, what's the degree of that thing? 4th times n squared, 6, right? So it'll be a 6th degree over 6th degree, and they both just have a leading coefficient of 1, right? Because there's just 1s there, so what's that limit going to be? 1. And so the ratio test gives you no information. Does that make sense?
Yeah. Okay, so that's just a quick way to know you don't use the ratio test.
Right, so if you ever just try it and you get 1, then you know to stop. What I was saying before though is when you see this polynomial over polynomial, we usually just don't even bother touching the ratio test, it'll always fail. So, but it's a nice, simple example to show our test. So ratio test fails, and again, that doesn't mean you're done, that means now you have to go back to your earlier tests. So, let's just do it. N squared, so let me just point out here, we're asked whether something converges absolutely, right? Conditionally or diverges. This series is positive, so absolute convergence and convergence are the same thing, right? If it's positive, it's only when you get negatives coming in that you worry about conditional convergence. So we're really just going to be testing this or this for this one. So when you saw this, when we saw this problem last time, we would have said it behaves like what? Yeah, we'll use the limit comparison test. N squared over n to the 4th plus 1 acts like
1 over n squared.
1 over n squared. Remember doing that? And then we do the limit. It's crazy how fast. We go here again, this is sort of thing that would have been a week ago, you would have learned this, but now it was like yesterday. So, we got this, we take the series we're interested in, we divide by the new, or the terms of the series we're interested in, divided by the new series. And again, you can, you don't have to show all the work. I think it's pretty easy to see that's that, right? You're going to multiply that n squared up top. And what's that limit? 1. Okay, now let's be really careful. We got all kinds of different limits we take and conclude different things. You have to remember, you're not in the ratio test anymore, so 1's okay. We're in the limit comparison test. What do we want our limit to be? No, to be not 0, right?
Less than 1?
No, just non-zero.
Oh, it's-
Ratio test, we're looking for it to be less than 1 or greater than 1. When we do the limit comparison test, we just want it to be non-zero. So it's really, it takes a long time to get used to those differences. There's a lot going on. You have almost 24 hours to do that, so should have plenty of time. Try to hang in there. Does that make sense, though? I would make little note cards about each test and what things you're concluding, and then know which test you're in the middle of. So now, let me just say, now use the limit comparison test.
I mean, once we get to, so we're at n squared over into the fourth plus 1, and then we work our way over to 1 over n squared. At that point, when we see that it's n squared, can't we just assume that it converges instead of keep going?
No, you're going to be able to in the next test, but right now we're trying to conclude that you know how these tests work, these various tests.
Okay.
So as we get a little further along, we'll be able to sort of say that, and when if you see this stuff in differential equations, you'll be able to do that. But for right now, we want to make sure you understand this test, which is what you're really using here. Okay? And so again, the point is, you make this thing, but this is really just, you're thinking, okay, I think it behaves like this. This is verifying that they behave like each other by getting this limit. So you're just kind of concluding things. Because if it was, a more complicated statement, it's really easy to screw it up when you try to say, okay, this is going to act like this guy. So this is just kind of making sure everything's precise.
And I guess, so you know to keep going if you just see in the directions determine if the following converges
You
absolutely.
mean keep going after the ratio test?
Well, after you get to 1 over n squared, because,
Well, that's so this is the way you should think about it. You either did the ratio test and saw it failed, or else you saw polynomial over polynomial and knew the ratio test would fail. Okay, so either way you do that. Then you go to the next test. That test is the limit comparison test. And so the limit comparison test says, compare your series with something you know the answer to. Okay? So that's your first step, and then you take this limit every time if you're doing the limit comparison test. Then we finally do what? We get a limit that's not 0. We realize that the series we compared it to converges, right? And why does this one converge?
1's not equal to 0. Or
No.
P series because 2 is greater than
P series, yeah, with P equal to 2, right? And so now, non-zero limit of the ratios, this guy converges means that thing converged as well. So therefore, the series we were interested in converges by the limit comparison test. Okay? And I should say, we end up with absolute convergence since everything is positive here. So the comparison test only applies for positive series, and so you got to be a little bit careful. All right, let's try another one. Okay, so take a minute and try both of those with what I just said over here, right? First step is you can do the nth term test if you want, but you should also be thinking, can I use the ratio test? And so you want to use the ratio test if you see a factorial or an exponential. So, do you see a factorial or exponential here? And then let me just say, -1 doesn't count, right? It's not an exponential, it just goes 1, 1, 1, 1, 1, or 1, -1. So we don't consider that exponential. So, ratio test will fail with this one. I think I'll show it again just to confirm it, but it's going to fail, and so then you got to use another test. This one you should be able to get by with the ratio test. It should give you an answer. So try both of them. This one's harder, so if you get stuck with this one, just move on to that one and do this one. I'll give you a couple minutes, and we'll work them out together. I'm going to set the ratio test up on this one. Like I said, in practice, you wouldn't use it here at fail.
So why does, let's see, where was it? Why does -1 to the n+1 power cancel with -1 plus 2?
Well, it's not that they cancel, it's that, I mean, so they cancel and would leave you with a -1,
Yeah,
but you're taking the absolute value.
okay.
And so my thought when I see it is just I'm just gonna ignore those because I'm taking the absolute value. So I just want, I'll get just the positive. Does that make sense?
Oh, because it's just one,
Yeah.
doesn't matter.
Right. So, I mean, you could, like I said, you could have said this cancels with that, right, leaving you with a -1, but you're taking absolute value, so it's just 1.
Okay.
And so we get to here. So again, you can skip this in practice, but if you did it, you get to here, now L'Hopital's rule would apply, right? You have an infinity over infinity, and so what would you get?
So just
1 over n plus 1 over 1 over n plus 2, which is 0 over 0, but don't use L'Hopital's rule again, just rewrite it.
Is it n plus 2 or n plus 1?
Yeah, which is 1, right? And so again, this was the ratio test, equaling 1 means it failed, so it gives you no information. So then you have to move on. Like I said, in practice, you should probably not have done this. You should skip it when you don't see a thing. Okay, so our first step is to determine if something converges absolutely, right? So converging absolutely means it converges if you take absolute values. So we check that first. If that fails, then we check if it converges conditionally. So and they'll give us a little roadmap here. So we first check for absolute convergence. And again, on the previous example, there was no difference between convergence and absolute because our function was positive, or our series was positive. And I'm going to need more space here, so I'm going to box that in for now. Okay? We'll come back to that. So we first check for absolute convergence. So we're going to look at this series with absolute values around it. And so when you take absolute values, the only result is that you can ignore that -1, right? It just becomes 1. So it's 1 over log of n plus 1. Again, the bounds don't really matter. We're just assuming, right? It really matters what happens in the end. So does that series converge or diverge?
By the limit.
What's that?
If we take the limit,
Oh, if you take the limit of 1 over log of n plus 1, it's 0.
converge.
No.
That's
Remember, being
Yeah.
non-zero means it doesn't converge. Being 0 doesn't tell you anything. It's the same mistake that everybody makes. Though. You're making
it's
this.
less than 1, isn't it? If you just plug in 1 over the natural log of 2 would be less than 1, right? So does it converge?
No. So you got to start thinking about things. So what are the series we know about convergence or divergence? We know geometric series, and we know p-series. So if the ratio test doesn't apply, you're going to have to do some version of a comparison test.
What if we use the alternating series?
Well, we can use that, but what does that tell you? That tells you, so we're going to use the alternating series test to conclude that this converges, but that doesn't mean it converges conditionally or absolutely. So we first have to consider it without the -1, decide if that converges or diverges. Once we know that, then we can come back and use the alternating series test. So the answer to this one is going to be conditional convergence, but we have to show this diverges first. Any thoughts about that?
So, if we had, well, how exactly does it diverge?
That's what we need to show.
Okay.
So the things we know about convergence or divergence, we know right, p is less than or equal to 1, that guy diverges. That's the closest thing you have. I know the log can be ugly, but there's no exponential, there's no factorial, there's no, so the geometric series doesn't make sense to compare to, so you're going to have to use some p series. What does log do? It grows really slowly, right? It goes off to infinity, but really slow. And so 1 over log is going to be bigger than 1 over the thing inside the log. log's smaller than n, so 1 over log will be bigger than 1 over that. Now, what do you think about that series on the left, or on the right, the 1 over n? Does that converge or diverge? Diverges, and again, it's not exactly a p-series, but you can, that's a p-series, right? It's a first-degree polynomial. If you add that up, it'll diverge. And so, I would just say this diverges, and I think you can just say it's a p-series with p equal to 1, as long as you realize it's a first-degree bit, and you're just one term ahead. That's the only difference. And if you think of if n goes from 1 to infinity, rather than being 1 plus 1/2 plus, you're starting at the 1/2 plus 1/3, but still that tail end is gonna be too big. So this diverges. This is bigger than a divergent series, and so it diverges by the comparison test. Therefore, diverges. By the comparison. Okay?
So here we don't get 2 points out the Dirac's or limits
What's that?
of the Dirac's comparison test.
Oh, right. Yeah, when I say, I always just say comparison to the direct. This is the direct comparison. Okay, so what have we shown so far? We've shown that if we take our series, we take the absolute value of it, we get a divergent series, right? So we haven't shown that the original series diverges, we've just shown that it is not absolutely convergent. Does that make sense? And so that'll be our next. I guess I really underestimated how much space we needed. So I'm just going to write this out. You don't need to necessarily include this line. But so our series here is not absolutely convergent. So now we might have the possibility of it being conditionally convergent. And so this is really the one place where that alternating series test is going to come into play. Okay? So, next, check if conditionally. Okay. And so again, that's just use alternating series test if possible, right, if it's applicable. So what was the alternating? Well, so first of all, you first need to make sure you have an alternating series, which we definitely do here, right? You get that -1 up top. And so what was our thing with the alternating series? You looked at the Bn 1 over that, right, where you drop the -1. That's a positive series. What things did we have to check? Its limit goes to 0. Then goes to infinity of that. That is 0, right? So that was the first step. That's essentially the nth term test part of it. And then what do you check next? That it's decreasing. And this one's pretty clear. Bn is decreasing, right? You're just going to add more into the log, which grows, and so the whole thing's decreasing. And so by the alternating series test, this series converges. And I'm going to just say conditionally. You got to be careful here. Right. The only reason we can say conditionally is because we've already determined it wasn't absolute, right? So the alternating series test just says it converges. It doesn't guarantee that it's conditional. It's only conditional if you say, by the alternating series test, I have convergence, and I've already shown it's not absolutely convergent. So you got to combine those two things to get there. I know it's a bit much to take in. But. Okay. So let's try this last, or that other one there, C. Squeezed in over there. Let me just rewrite it. This will hopefully feel refreshing after that last one, which is a bit of a mess. So, again, when do you use the ratio test? If you see factorials or
Extra.
exponentials. There's an exponential, right, 5 to the n. So ratio test should work. So we try our ratio test. In this case, what do we have? Absolute value, -1 to the 5 to the n plus 1 over n plus 1 to the 5th, right? Times reciprocal. Okay, you can do this however you want. You're taking absolute values, again, drop the -1s. The 5 to the n and 5 to the n plus 1 cancel and leave us with a 5 where? Numerator. Numerator, good. And so I like to just do it like this. I get a 5 in the numerator, and then I just put the rest of it next to each other. Does that make sense? The polynomial parts. Because those never cancel nicely, but their limits are always nice. So what's the limit now of this?
Just 5?
Yeah, the 5 sits there, and then 5th degree over 5th degree, right, with coefficients of 1. So 5, what test was this?
Ratio?
Ratio test, so what do we do with the 5?
That's greater than 1?
Greater than 1, so divergence. Therefore, series. Divergence. Does that make sense? Okay. So we definitely will have to do more of this, especially this bit with conditional convergence and stuff. It can be a bit of a headache. We'll do some more examples, but let's talk quickly about the root test as well. Okay. So again, it seems like we have to memorize a bunch of tests here, but the root test is exactly the same test as the ratio test, except for, and I'm just going to jump ahead. Okay, we got a series. So rather than taking the ratio of the series, you just take the nth root of the absolute value of the nth term. Okay? So same setup, and then conditions are exactly the same. So if L is less than 1, then the series with the a sub n's converges absolutely. All right. L greater than 1. Series diverges, and L equal to 1. And I'll just say this too, right? If you think about this one for a second, when n gets big, this gets really close to L. Take the nth root of both sides. A sub n gets really close to L to the n. So if n is less than 1, you're going to have a geometric series here, right? And if n is greater than 1, you'll have. And so you basically, it's basically the same proof as the ratio test to prove it. Don't worry about it, but there's certain situations where this is much more useful than the ratio test. So they're kind of interchangeable. You can prove one with the other, but that makes sense. There are definitely times where this is valuable. And so, okay, so this time just converge or diverge. Let's not worry about the absolute convergence. And again, this test only concludes that. We'll start with one that's basically for free if you know the root test. Okay? So here's a series. A bunch of stuff's happening, right? You're getting close to 3/4 on the inside. You're raising it to an infinite power, right? And so there's some hope that it converges because you're getting a number smaller than 1 and you're raising it to this power. So maybe this thing converges, but let's just see. And so this root test is exactly what we want if your whole thing is, right, some term to the nth power. The root test just takes the nth root of that and it'll just disappear. So that's the one place where you really want to take advantage of this. So we take the nth root of series. And again, absolute values here are unnecessary. This thing's positive, but if it wasn't, just use that. And again, most of the time, all you're doing with the absolute value is ignoring that -1. Okay, so what's the nth root of the nth power here?
3 over 4, 2 over 4.
They just cancel out and you just get that, right? What's that limit? 3/4. Compare it with 1, it's less than 1. And so, absolutely convergent, right?
So does 2 over infinity just get a 0?
Yeah.
That's what 3/4.
Yeah. This guy, I guess I forgot to say by the ratio test on the earlier ones. You really should say that. I'm not too picky usually, but I'll say it on this one. Converges by the ratio, by the root test. So on those ratio tests, you should really put a line at the end to say that you used it. Usually as long as it's clear that you used it and then you concluded stuff. I'm not too picky about it, but formally you probably should make sure to add that in. Okay, any questions on this? Okay, well, do the homework from this section and then we can talk about any other stuff. Move on, I guess.